This is 7.3, special products of polynomials. So if we have the square of a binomial term, that would be a plus b squared. So that would be a plus b times a plus b. Then if I FOIL that, I'd get a squared plus ab plus ab, because ba is the same as ab, plus b squared. And then combining these like terms in the middle, I get a squared plus 2ab plus b squared. So you'd have each squared term, each of these terms squared, and then 2 times the product of those. Now if I have a minus b squared, that's a minus b times a minus b, that would result in a squared minus 2ab plus b squared. So we're going to find each product. So if I have x plus 3 squared, that is going to be x plus 3 times x plus 3. And when I FOIL that, I get x squared plus 3x plus 3x plus 9. Combine like terms, x squared plus 6x plus 9. For x minus 4 squared, that's going to be x squared minus 8x plus 16. Here's another example. This one shows what's going to happen when there's a coefficient in front. So that would be 9x squared plus 24x plus 16. Here I have 2 different variables, and so that's going to be 36x squared minus 24xy plus 4y squared. It's okay to leave this y squared at the end in this form. So if I have one that is adding and one that is subtracting, a plus b times a minus b, I'd get a minus ab and a plus ab. And that makes 0, so that's just a minus b squared. So let's look at one with some numbers. X plus 10 times x minus 10. That's going to be x squared minus 10x plus 10x minus 100. So minus 10 plus 10 is 0. So I have x squared minus 100. Here's another one. 3x plus 5 times 3x minus 5 results in 9x squared minus 25. And on this one, they're in different orders, but we're still going to get 4x squared minus 81. And another one. If we have x squared plus 4 and x squared minus 4, square your first 2 terms, x to the 4th, and square your second terms, minus 16. So another way to do this is to organize it with a box, where you put one polynomial across the top and the other polynomial across the bottom. Then you multiply x times x, and the product goes in the box where they would meet. Your like terms will be formed on the diagonal, and then when you combine those, you would put that in its spot. And we can do this with polynomials of all sizes, and it really helps organize everything and keep you from getting lost or losing one of them. So you can see here a trinomial by a binomial, and we'd get the same thing. Alright, so let's say a combination of 2 genes determine the color patches of a border collie, a dog. The offspring has an equal chance of inheriting one gene from each parent. The gene capital B is for black patches, R is for red patches of fur. Any combination with a capital B will result in black. The Punnett square shows the possible combinations. What percent of the possible combinations result in black patches? Then we're going to show how we can use a polynomial to model the combinations. So here's the Punnett square that we are given, where we have capital B and a lowercase r. B times B is B times B. We have BR, BR, and RR. So anyone that has a capital B will be black. So 3/4 of the squares are black, so that is 75%. Now for B, this would be an equal chance for each gene from the parents, and we have 2 parents, so it's squared. When I FOIL that, I will get 0.25b squared plus 0.5br because that would be 0.25 BR plus 0.25 BR, makes 0.5 BR, and then plus 0.25 R squared. So this means that you have a 25% chance of getting capital B, 50% chance of getting BR, and 25% chance of getting an RR.